Hi everybody and welcome to today's webinar. We are glad to present you the webinar Build a Predictive Maintenance System with AWS Greengrass. The webinar is presented by our partner SAM Solution. First, a few things about its organization. At the webinar, we will have a Q&A session at the end. You are able to type your question in a question box of the webinar tool already while the webinar is ongoing. You can use the chat box also to let us know about technical issues like sound, video quality, or more. This webinar is recorded and we will make the webinar online available approximately in a week or two. Let's start. I'm glad to introduce Julia, Andre, and Dimitri from SAM Solution. My name is Diego Bienz and I am Field Application Engineer at Toradex. I am working in our office in Horb. Before we dive in technical details, I would like to give you a short introduction of Toradex. We are specialized on ARM-based system on modules, also called computer modules. We have in-house hardware and software developers. Mostly we focus on Linux, but still support Windows CE solutions. Our board support package is in production quality and you are able to take it and work with it for volume production. We provide at least 10 years of product availability. Our products come with free support for the lifetime of the device. We do direct sales, so we don't work with distributors. What is Toradex? Toradex was founded at 2003 in Switzerland. Now we have more than 3,000 active customers worldwide. We are a fast-growing company and now we have more than 100 people in 9 countries. For support beyond, Toradex provides free base support packages support and we have more than 45 proven partners. Our headquarters is located at Horb, near Lucerne in Switzerland, and we have 8 more offices over the globe. Our products are used in various types of application, like communication, medical and healthcare, laboratories, building automation, and more. We have 2 product lines, Apalis and Colibri. All modules are pin compatible within the family, so you can easily replace modules without carrier board redesign, even if another module has a completely different processor. As you can see, we have sums based on various system on chips from NXP and NVIDIA, like the IMX6, IMX7, IMX8, Tegra 2, 3, and K1, etc. Colibri has a lot of industrial buses like SPI, CAN, I2C, etc. But it lacks high-speed interfaces like PCI Express, USB 3, LVDS, and the others. So we introduced the Apalis family. But they are not meant to replace the Colibri modules. So you have the ability to choose depending what features or interfaces are required for your application. Now I'm going to hand over to SAM Solution.
Thank you, Diego. Hello, everyone. My name is Julia, and today I and my colleagues Andre and Dmitry are representing SAM Solutions at the webinar. We'd like to introduce a predictive maintenance system that we have developed on a Toradex board to you. Andrei Andrianov is a senior software developer, and he will provide a live demonstration of the system and address all technical matters. Dmitry Koshkin is a business development manager, and he will handle all commercial questions. I am a senior marketing specialist, and now I would like to give a short presentation about SAM Solutions and brief you on its key competencies and expertise in the development of IoT, system, and embedded solutions. For 25 years, we have been creating IT solutions for companies from all over the world, while focusing on businesses that operate in the DACH region, the US and UK. Currently, we work with more than 70 customers. To name a few, we have created solutions for IBM, Daimler, Siemens, Fujitsu, SAP, and others. Our company has more than 600 employees in its offices and delivery centers spread across Western and Eastern Europe and in the US. The headquarters are in Munich, Germany. We provide full-cycle software development services that encompass all stages of custom software development. Depending on the project's specific requirements, we develop end-to-end solutions, deliver dedicated talents, or provide managed services. In addition to software engineering, we specialize in e-commerce, content management, the Internet of Things, and mobile apps. To ensure that embedded software operates smoothly as part of an IT environment and to encourage efficient functioning of connected devices, we provide system and embedded development services. Our IoT development projects are based on a thoroughly elaborate infrastructure that embraces all layers and components. We focus on smart homes, manufacturing, the automotive industry, as well as solutions for biometry-based protection of buildings and facilities. That said, our infrastructure can be successfully implemented in a variety of domains. Our team has created a predictive maintenance system that analyzes the state of a board motor. The system collects motor performance parameters, transmits them to Amazon Web Services, and applies machine learning algorithms to identify the motor state based on Amazon Greengrass and Amazon Lambda technologies. Thank you for your attention, and let's proceed to the technical part of the webinar. Now I'm turning it over to Andrei. He is going to provide a live demonstration of our predictive maintenance system and tell about its capabilities and specifics. Andrei, over to you.
Thank you, Julia. Hello, everyone. It's a pleasure to see all of you here today with us. My name is Andrei, and in the course of this webinar, I will introduce our predictive maintenance system based on a Toradex board to you. So let's get started. Let's start from the concept. As you know, no modern production process is conceivable without electric motors, regardless of the industry. So we have set our sights on the creation of solution that assesses the behavior of a motor and, based on that, determines the status and alerts about aberrations if they are any. For this project, we were tasked with building the prototype of a predictive maintenance system that specifies the state of a motor based on its vibration frequency and force. In our prediction concept, we were guided by the fact that the abnormal motor vibration level signals that it is probably out of order. To specify the state, the system requires data that is typical for each of the device states. When it behaves normally, which means that it operates within normal operation boundaries, when it is turned off, and when failure comes. For example, if the main shaft is bent, the motor vibrates and produces fluctuations that are different from those typical of the normal state when the motor is balanced. Our tasks we've faced during the development of this project, there are two of them, practical and technical. So from the practical perspective, businesses need to continuously monitor their production assets, including machines that are remotely connected to the network. Also equipped with the alerting functionality, the solution reports any aberrations from slight malfunctions to device outage. In the technical context, we were tasked with getting the most out of modern technology to enhance the monitoring of the motor state. That is why we relied on AI methods for the detection of abnormal behavior and based data analytics on a pre-trained model. Also, we've implemented simultaneous algorithm updating across all devices in the network, which enables better visualization of the result and provides real-time data. what concerns the specifics of traditional solutions, if companies opt for one of the traditional solutions that are not related to the cloud, they should provide a number of specific conditions. They need to ensure that software is developed and working in a protected environment that features its own infrastructure, data collection, and analytics. Also, traditional solutions require dedicated servers for successful updates, while the maintenance and support of these solutions cannot exist without hiring, for example, of dedicated employees, which may cause overstaffing. Along with the requirements that companies have to fulfill, the, so to speak, no-cloud solutions involve certain disadvantages. They don't provide efficient system monitoring, and at the same time, they are quite time-consuming and may come quite a high cost. Also, algorithm maintenance is complex enough, and if an algorithm fails, prospects are slim that it can be stopped or reloaded. Let's switch to the specifics of cloud solutions. For our predictive maintenance system, we have opted for cloud technologies as they provide significant advantages. Unlike traditional solutions, the cloud enables streamlined software development, updating, and monitoring, enhanced security and flexibility. When choosing a cloud solution for our system, we decided to use Microsoft Azure and AWS, Microsoft IoT Edge, and Amazon Greengrass, respectively. You may have a question, why both of them, not just one specific cloud solution? We were looking to create a flexible system that supports the interchangeability of cloud services so that it can fit all companies, regardless of whether they rely on Microsoft or Amazon. That is why we trained our system on Azure while we used AWS for the deployment. So the platform interaction scheme can be presented as follows. Here you can find the visual representation of the whole process. So on the left side, you can see that we've attached a vibration sensor to the brushless DC motor. The sensor acquires vibration data from the motor and transmits it to the Toradex development board. On the board, we've deployed Amazon Greengrass that analyzes the state of the motor in real time. It recognizes three states: an off state when the motor is stopped, normal state when the motor is on, and an abnormal state that indicates malfunctions such as under voltage, over voltage, or something else. The model used in prediction can be deployed to an IoT-enabled or edge computing device using different ways depending on the requirements. It can be accessed through Amazon S3 services, Azure Cloud Storage, and so on and so forth. So then the boards finally reports the motor status via a web interface or using various communication protocols such as MQTT, SMTP, etc., which depends on a company's business requirements. So let's switch to the perform training. The training process includes 3 steps. First, we've collected parameters that are specific to each of the states: when the motor rates, when it's stopped, and finally when it performs normally. Later, we've trained the model based on the above-mentioned classification. So, data collection based on the MPU 6050 sensor by InventSense, which you can see on the picture. And also, as you can see, it is this is a specific sensor uses I2C interface. In case you need SPI interface, you can use MPU 6000 model. So let's switch to the prediction process. The prediction process works as follows. The data that is the sensor collects is sent to the pre-trained model. Since each data set matches a specific class, normally it's 0 or off, OK, or number 1, or 2, which means fail, the model parses the received information and ranges it in accordance with these statuses. Then the result can be displayed either on a web page or on an LCD or via one of the communication protocols. As you can see, the communication works as follows. we can seamlessly switch between each states without any trouble. So it means when we, for example, enter the fail state, we can later enter either off or OK state. It just depends on the data and the state of the motor. So let's switch to the video presentation to show how it works in almost real life. Just a second. So as you can see, the system consists of two parts: the board itself and a sensor, which is attached to the computer fan. As I've mentioned earlier, the connection interface is I2C for MPU 6050 and SPI for MPU 6000. Everything is wired to the Calibri board using Arduino pin pads, which, as you can see, is the prototyping process. And the sensor board is placed on top of the CPU fan and is secured on a mounting tape. Now the model predicts that the motor is turned off, and soon I will turn it on, turn the power supply on to make the motor spin. So the prediction level is 99.6%. This is the response from the model, which runs on the Toradex board in the secure environment provided by the Amazon Greengrass. So I turn it on, and as you can see in this model, the model predicts that the motor is spinning correctly without any structural changes. You see that the prediction level is almost 100%, so it's pretty accurate. And in a few seconds, I will increase the voltage level to the critical value of 20 volts, so that the motor will spin really fast, which in our case will mean that it works abnormally in an overvoltage situation of overvoltage. And as you can see, the model says that the motor is in fail state, an overvoltage. So the model also says that it's 100% of failure. It's sure that the motor works abnormally. So now I will decrease the voltage in order not to burn the motor. So we are almost back to the normal operation mode, 12 volts. And another example I would like to show you is the situation when the obstruction happens. So in order to show you the obstruction situation, I need to put the rubber. You can see on the top left level. So as you can see, the model detects obstruction itself. So 12 volts is normal operation mode, but since the obstruction is on the blades, so it shows that the obstruction is detected, and it's also in fail state with the prediction percentage to 100%. So now it went back to normal. So the concept, as you can see, is working correctly. Let's switch to the presentation. So next comes the computer on model. We've based our prototype on as the framework for the development of a predictive maintenance system. We used Toradex NXP IMX6 ULL computer on model called Calibri IMX6 ULL, which is based on an NXP CPU, which is also has optional support for wireless interfaces, Wi-Fi 802.11 AC and Bluetooth 4.2. In case you need to communicate, for example, with mobile application or another computer in the situation you don't have a wired connection or so, it's pretty useful. Also, connection interface is SODIMM compatible. As for me, the main feature I should mention that the model provides LTS support till 2028, which for me is pretty convenient in case of industrial usage. also its operational temperature ranges from -30 to +85 degrees Celsius, so it's pretty wide. And next comes the sensor itself. I've mentioned it previously, it's MPU 6050 by InventSense, which combines two devices under one hood. It's 3-axis MEMS gyro and 3-axis MEMS accelerometer combined with the digital motion processor, DMP. And this sensor provides pretty enough of accuracy for gyro and accelerometer, which can be configured easily using the appropriate software. Also, it has low power consumption in an active mode, and possible usage of either ITC or SPI interfaces, depending on the needs of the project. So it's almost end, and I should try to sum up the project results. First of all, we've developed an efficient prototype, I think, of a predictive maintenance system that features a high probability of prediction results. You saw that it ranges from 85 to 99, almost 100%. For model training, we successfully applied algorithms that are based on AI, particularly TensorFlow and Keras frameworks. Also, we've made active use of innovative IoT technologies powered by Amazon, which allowed us to build a high-performance system that provides accurate predictions. And we've made heavy use of Toradex board that proved to have all the required characteristics and capabilities, allowing us to enable predictive maintenance system. So, thank you very much for your attention. That's it.
Okay, thank you. Then we are already in the Q&A session. For the questions already popped up from your presentation. So the first question would be to use Sam's solution. It's called, is there a potential to scale the demo solution to more complex multi-sensor systems? And what are the options and constraints?
Of course, there is always space for finding an optimal and more precise solution. And in our case, I think this system can be easily extended using additional sensors like microphones, for example, optical sensors, just to give precise data from different sources, especially, for example, to use voltage level sensors to additionally detect the state, maybe the speed controller, which shows the speed of the motor, for example, to control for example, if we are powering the device with its normal voltage and something happens, to help the model predict correctly the situation when something goes wrong, we can use the results from the model as well as the data acquired from voltage and Hall effect sensors and use it in the business logics. It just depends on the specifics of the project itself and requirements for this specific project. This is what I think.
Okay, thank you. Another question was, which model did you use on IMX6 ULL and which inference engine to run it? So which framework? Maybe also you could answer this question.
The model used for this solution is based on CNN. We've designed created this model using Jupyter notebook, and it is based on Keras frameworks. Both Jupyter and Keras exists on Azure and Amazon. So the main feature, maybe I think that's important, that we can use the algorithm to create this model on either Azure or on Amazon. So this also can be pretty convenient depending on the customer needs, because some customers require this project to be implemented using Azure platform. Some customers require Amazon. So we've proved the concept that it can be easily generated on both of them without any problems, and can be transferred between them easily. So this is the idea.
Okay. Thank you. So another question was, which other Toradex hardware can be used for this demo application? We have several models of hardware which you could use for such cases. The Colibri IMX6 ULL is a model which from the Colibri family, which provides less interfaces than the Apalis family. And you could possibly use a lot of hardware models we have for such a demo, because the requirements to the interfaces are not that high. You are able to search for products and also to filter your requirements of your products on our web page, which we shared with you in the chat. And there you are able to see all the hardware we provide. For this demo, I think a lot of hardware would possibly go with. First of all the Apalis family, I think, would be able to do such a demo. And also in the Colibri family, you could use other boards like the IMX7, I think, other models from the IMX6. And for future, we also have the IMX8 on the Colibri module. The IMX8X will be on Colibri, and we also have the IMX8M on Apalis family, which you could use for such a demo. But it always depends on what your requirements are, and then you should choose the best fitting hardware on our web page. So another question we have here. Maybe also for SAM solution, a question: was it required to tailor the inference engine to the ARM architecture?
I think that maybe it's a good idea to write the question to the email directly, because
okay. Then we will answer this question later via mail.
Yeah.
Okay. Yeah. Perfect. So, and the other question is it possible to get full demo for testing in my Apalis TK1 to share the code? I think is this question.
Yeah, I think it is possible. Also,
so we'll also follow up via mail, I think, for this question, for the code. Another question is, since IMX7 is an ARM A7 with Cortex M4, do you have plan to run AVS RTOS on Cortex M4, so on the microcontroller M4? Is it possible to run AVS there, the AVS RTOS?
It really highly depends on the possibility of run the green grass itself on the CPU, because we're a little bit limited with the environment. And for example, again, it is possible not to use the green grass itself, but as a result, we will be limited with the update functionality. So if Amazon will implement the support for the specific CPU, then the running of this project will be possible on the specific CPU. I mean, with the Amazon functionality, not as a standalone.
Yeah, okay. I will follow up with another question. So, does the solution have potential to scale up the machine learning concept? And what are the constraints? And can you give us the example of such cases?
Yeah, sorry. Yes, I think that surely can be extended and scaled because it is possible to implement such functionality when the model can be trained by itself. But it will require much more effort to do so, but I assume it's possible. I mean that the model can acquire all the data needed to work correctly, then to, for example, again using Amazon or Azure solutions, to update itself using new data and to make the prediction results more precise or to add additional functionality. But in this case, also the assistance of pre-trained staff may be required, for example, to update the Lambda itself, because the algorithm consists of two parts. Lambda, which means this is the code written either on Python or Node.js or, as far as I remember, Java, which is deployed from the Amazon's web service to the board itself using Amazon Greengrass services. And this Lambda runs the model itself and gets the prediction results from the sensor. I'm sorry, gets the data from the sensor, passes this data to the model, and provides the prediction results to the web interface or other interface required by the solution. So in this case, assistance will be needed to check at least everything is trained correctly and the prediction results are correct. So, but yes, it is possible. But I cannot show. Yeah. Okay.
So another question is the MPU 6050 sensor you showed is working under I2C. Therefore, what is the accuracy of the actual vibration due to data sampling frequency?
As far as I understand the question about the delays of the data acquisition. So as far as I remember, it's nearly one package which consists of 6 values from 2 sensors. Each sensor transfers the data split by 3 axes, X, Y, and Z, for each sensor. And so we get all 6 values from the sensor. And it's nearly 2 microseconds, as far as I remember, between the packages. It's first of all, it's highly dependent on the speed of the I2C interface also, and there may be the possibility that there will be some slight delays and some packages might be lost, say 1 or 2, and I think that in case of our sample, it's not so important to lose 1 or 2 packages. It's just an example, but in case of real system, it will require, of course, real-time operation, more precise sensors, and other types of interfaces, like maybe SPI, which communicates at a higher speed rather than the I2C itself, which I2C is 400,000 400 kilohertz, and SPI, as far as I remember, will be possible to use more than 10, maybe megahertz. So the results will be provided a little bit faster than I2C, and in this case, just depends on the situation, of course.
Okay. Thank you. We have a few questions about this inference engine. So the first, was it required to tailor the inference engine to the ARM architecture with the ARM compute library? This was the first we didn't really understand. So we have explanation here. ARM compute allows to deploy inference engine from TensorFlow model and have it optimized for a given ARM architecture. Clarification for the question before. As part of the ARM Trillium project for embedded ML. So now the question is, could you give some details on the deployment of the inference engines from the cloud to the device? Does it allow easy and light differential updates of an already deployed model? Or does it require full engine redeployment each time the engine is iterated upon?
The situation comes that the model itself, when it's deployed, it can be updated only when the model itself requires another training. But in other cases, you don't need to redeploy the model a few times. You just deploy it, and it exists in the Lambda inside the sandbox, say. So it exists there. But if it's maybe it's not the full answer, maybe you need to better to ask this question using email, so I could try to give you more wide answer.
Okay, so just if this answer wasn't in deep enough, just write us and we can clarify this via mail again. Yeah. Another question was about the prices of our system on modules, and this is actually pretty simple. All our prices of the system on modules are on our web page in the web shop, transparent for everyone. The prices depends on the number of sums of the system on modules you order from us, but you can see all the prices in our web shop on toradex.com. So next question is, the Lambda function you deployed on the IMX6 ULL was a specific parser for the model you used, or is it a generic parser?
Actually, the Lambda function itself is kind of specific code, because in general, Amazon supports a few kind of triggers which trigger the code inside the Lambda function. So in our case, we didn't use the default trigger for Lambda function. We wrote the code which starts immediately after the Lambda is deployed and started for the first time, because there are some limitations also, because the Lambda itself is running inside a sandbox, which has also some settings maybe you perform on the web page on the Amazon console. For example, you provide the time for how long the Lambda function must be executed, and after that the sandbox will kill this function. Or another option is you can execute this function using some event. For example, when you upload something to S3 Cloud, the monitored folder, so-called folder, from the Lambda itself, if it finds that something uploaded to the folder, it can trigger the function itself. So in our case, we didn't use this also, because we needed to run this function continuously, and that's why we've written the code, and that starts immediately after the deployment of the Lambda. And then we used we loaded the model using Keras framework, and later we just passed the data from the sensor to the Lambda to the model using Keras API, and got the results from the model. So each set we've provided to the set of data we've provided to the model returned for some data in response. Normally, this data is presented like dictionary, maybe. It contains of 3, in our case, fields, 3 values in array. Each value is represented as a float number, which is kind of the prediction of to which class the provided data might be belong to, because the model is not sure of 100% that this data might belong to some specific class. So this is pretty simple, at least in our case.
Okay. Thank you for the clarification. Another question is, do you deliver to customers only in Europe? That's not the case. We actually deliver all over the world. You just can order via our web shop and we deliver it to you in any country. So I think maybe a last question to SAM solution. Yes, I have here another one. Why you use near real-time processing in the demo? Is there an option to go real-time, let's say for industrial IoT scenarios?
Yeah, sure. It's possible to go real-time, but in this case, it is required to use some kind of pre-kernel firmware. It is possible to use the pre-kernel firmware. It's kind of operation system before operation system, which makes some specific parts of the maybe code or accessing the hardware in real time. So it's kind of, how to say the example, everyone knows the UEFI engine in laptops. It's a new version of BIOS. So everyone also knows that UEFI, instead of previous version of BIOSes, still persists in the memory after the operation system has loaded. So in this case, regarding the solution of the RTOS or real-time solution, the pre-OS level will provide real-time operation, while the OS level will provide user space communication. So the data will be acquired in real time, while the user interface and some specific applications needed to work for this specific solution will work in the user space in another kernel.
Okay, thank you very much. So we are at the end of our webinar. I would thank you for attending the webinar. Also a great thank to SAM Solution for the great demo and the presentation. And I wish you all a great day and see you next time. Thank you.
Thank you. See you.